Hi guys, today we're doing logarithmic and exponential equations, and as you can see I have the rules listed on the left hand side of the page. These are rules that have been built up throughout the chapter and as we've learned about them, and you'll see how we use them and when we use each one. And we will also be using the properties of logarithms that we practiced last section. Let's go ahead and get started with the first question. With this first question, we see that we have a log equal to a constant. And so with this question, we will be using the red equations to help us. When we see a single log equal to a non-log on the other side, we're going to rewrite this as an exponential equation. And as we can see, the base of the log is 3. So we're going to use that as the base of our exponent. Then 2 is our power, and then our argument becomes the other side. And then it's just a matter of simplifying each of these terms to isolate the x. So 3 squared becomes 9. I added 1 to both sides. And then I divide both sides by 3. And I get the answer 10 over 3. And that is our preferred way of writing the solution. We don't want to take time to write it in mixed numbers. We prefer this improper format. And also, I don't want any decimal approximations when you have a nice rational answer like this. So 10 over 3 is a great answer. Now before I can say that's my final solution, I do want to check that taking this answer and plugging it into the argument makes my argument positive. That is, with all logarithmic equations, the argument must always be positive, and for all logarithmic and exponential equations, our base must be positive and it cannot be equal to 1. So we have those extra rules written on the side as well. So let's go ahead and take this and check. And as you can see, I took the value of 10 over 3. I took that and plugged it into our argument. And when I plugged it in, I get the value of 9, which is a positive number, so that's valid. So I can use 10 over 3 as my solution. And you write your solutions in set notation. Looking at question number 2, we see that we have a log equal to another log, and so a single log on each side. So we can actually use the rule that's written in purple, where when we have that situation, we take out the arguments and we make the arguments equal to each other. So this would just become 2x plus 3 is equal to 3. And solving this is very easy. You just want to subtract 3 from both sides and then divide by 2. And 0 is not positive, but it doesn't matter the value of 0 of x itself. It matters what happens when I plug that in. So we're going to take that and plug that into our arguments and make sure that those are valid solutions. So you can see that when I plug 0 into my argument, I get the value of 3. And 3 is positive, and you can't plug it into the other argument because that argument doesn't have any variables. The argument's just 3, so we don't have to worry about that second one. And so this is a valid solution because it made our arguments positive. So there we go, writing our solution in set notation. When I look at question 3, I see that it says log plus log is equal to 2. And that's not in the correct format to be able to use one of our rules on the left. It needs to be a single log on the left and a constant or single log on the right. And I have multiple logs being added. So we want to refer to the properties of logarithm and figure out how to combine that. And when we are adding two separate logs, then we end up multiplying their arguments in the same log equation. So you can see that I used brackets to put the x times the x minus 21 in the same logarithm. And now I have this written as a single log is equal to a constant. Let's go ahead and simplify the inside of the logarithms right now. I just thought it might be a little bit easier to multiply out the inside so I don't have to use brackets. It's a little bit cleaner to look at. When I look at this log, I notice that there's no base written, and when there's no base written, it means there's an invisible 10. And so we're going to use that when we rewrite this log. And you notice that I have a log equal to a constant. We're going to use the first rule, the one in red, and we're going to rewrite this as an exponential. The base of our logarithm is 10, So we're going to use that for the base of our exponent. We're going to put it to the power of 2, and then we're going to make the argument go on the other side. And then solving this just as a matter of simplifying. 10 squared became 100, and then you want to set it equal to 0 so that you can isolate all the terms and factor the quadratic. So you can see I got two solutions. I have x equals 25 and x is equal to -4. So we want to take that and plug it in to each of our arguments and see if those answers are valid. For x is equal to 25, we plug into the first argument, which is x, and we just get 25, which is good. We plug into the second one, and we get 25 minus 21, which is 4, which is also positive, so that's good. So 25 is one of my solutions. Let's check on the other one. When we look at x equals -4, we plug it into our very first argument, and it ends up with a negative, so that's not okay. So we're going to cross out that as one of our solutions. So our solution, even though we found two answers, we're only going to use one as our solution, and that's going to be 25. No matter what the solution looks like, you always have to test it into each of the arguments to make sure it's valid and that it fits into the idea of the domain of a logarithm. For question number 4, I see that it says log plus log is equal to log, and that's too many, and I need to use the rules to combine them and to condense them into one single log on the left-hand side. You should remember that that means that we take that addition and turn it into multiplication within the one argument. And then I'm just going to multiply it out within that argument to make it a little bit easier to look at. And remember, when you have log equal to log, then you just set their arguments equal to each other. So we're going to set x squared minus 2x equal to x plus 4. And then it's just a matter of solving this quadratic equation. Make sure that you write it equal to 0. And then after you factor, solve each one to find your two solutions. But before you write them as your final solutions, you do have to test them in and see if they are valid. You want to make sure that you test it with all three original arguments. So if I'm looking at the x equals 4, that gives me an argument of 4. It gives me an argument of 4 minus 2, which is 2. And it gives me an argument of 4 plus 4, which is 8. And all three of those are positive. So 4 is one of our solutions. Let's try it with x is equal to -1. And when I plug it into the first one, it's already negative. And so I don't have to test the rest of them because once it doesn't work, it doesn't work. And so we only have one solution. That solution is 4. When we look at question number 5, which is an exponential equal to a constant, and the variable is in the exponent, then we're going to use the rule in red to rewrite this equation as a logarithmic equation. And notice that the log will have the same base as the exponent. And so we will take the negative x will be equal to log base 2 of 1.5. And in order to solve for x, all we have to do is divide by -1. So you get x is equal to negative log 2 of 1.5. And when I look at this question, that is my exact answer. I'm going to rewrite this as negative ln of 1.5 over ln of 2. And then I'll use my calculator to find the answer. And if I know I want my answer to 3 decimal places, I always find 4. And then that way I make sure I round it appropriately. And so there's my decimal approximation. Notice that these are not two separate answers. It is one answer written in two different formats. We have the exact answer as negative log base 2 of 1.5, but that's value is negative 0.585 approximately. And so those are the same answers, just written in two separate ways. Question number 6 is a little bit intricate, and at first glance we might think, hey, we have an exponential equal to an exponential. All we need to do is grab their exponents. However, we can't apply the rule in blue because the bases are not the same. One side says 0.3, the other one says 1.7. So the blue rule doesn't apply here. And what we're actually going to do is say, you know what? I have variables in my powers here that I want to take out so that I can solve for them. And we're going to use some properties of logarithms to do that. So I'm actually going to use the purple rule, but in reverse. That is, if I have two things equal to each other, I can take log of both sides. And so I just took natural log of both sides because that's easier to write. And we have that rule in logarithms that if I have something to a power, I can take that power out of the argument and bring it down as the coefficient. And so that's the way I'm going to remove these variables from the powers. And so once you have it out of the powers and as a coefficient, then it's just a matter of multiplying out. And then you want to move all of your variable terms over to the left and all of your non-variable terms over to the right. So I'm going to do this step all at once, but I wrote my steps out in orange and green so you can see my thought process. I have x times ln of 0.3 minus 2x times ln of 1.7, and then on the other side I'm going to get minus ln of 1.7 minus ln of 0.3. After I have all my x terms over on one side, I'm going to factor the x out. So I get x times ln of 0.3 minus 2 times ln of 1.7, and the right hand side doesn't change. And then all I'm going to do is divide so that my x is isolated on this side. And it's a long and complicated answer, but thankfully we don't have to plug that in anywhere to check because the original question was in exponential form and the domain of exponents is all real numbers. So we're okay with this as our solution. This next question has an exponential equation, but it has multiple of them and then also a constant. And we're not able to isolate any of these pieces the way that it's written. And I can't combine them the same way I was able to combine logarithms. And so what I want to do here is do a little bit of creative substitution so that I can treat this like a quadratic equation. As you can see, we have 3 to the power of 2x, and we also have 3 to the power of x. And so I'm going to rewrite both of those as 3 to the power of x. And when I write it this way, you can see that it looks like a quadratic. And we're going to substitute 3 to the power of x out for some other variable. You can use any variable you want as long as it's not already in the equation. So I'm going to write this as y squared plus y minus 2 is equal to 0. And then I'm going to factor and solve. And when you write it this way, remember that when you solve for y was not in the original problem. So we need to substitute it back out for what it's equal to. So all of my y's will become 3 to the x. Now the domain of the domain of exponential problems is all real numbers, meaning my variable in the power can be all real numbers. But the range of exponential problems is positives. And when I see this, I notice that that's not positive. I get 3 to the power of x is negative 2. And there's no power that you can take this to make it negative. But if you don't know that at this step, you could take this and rewrite it using the rule in red. And so I would get x is equal to log base 3 of negative 2. And notice here, when I write it this way, my argument is negative, so that's not possible. So either way, you're going to end up throwing out that answer. We don't have a solution to come from this x. When I to the other side, we should recognize that we know the answer, but let's say we don't. Then I would get x is equal to log base 3 of 1. And that becomes x is equal to 0. And if I take this and plug it in, we should see that our answer is correct. We get 3 to the power 0, which is 1, 3 to the power 0, which is 1, minus 2. And so that's 1 plus 1 minus 2 is 0. That is correct. Our 0 is our solution. Keep in mind that question number 6 and question number 7 do use rules for exponential equations, but we can't use them right away the way that we want to with the rule in blue. What we actually had to do was take these and rewrite them in other formats like we've learned previously. And we solved this in quadratic form, and then after I solve for y, I have to make sure I solve for x again. The last question asks us to use a graphing utility to solve an equation. And it has an equation where there's a logarithm on one side and an exponential on the other. What I did was I took the left side, set it equal to y, and then I took the right side, also set it equal to y. If you have a graphing calculator, you would use your y equals button, and you want to type both of these in. I'm using Desmos, so I'm going to just show you the graph. This is the graph of ln of x written in red, and this is the graph of negative x squared written in blue. On your graphing calculator, there is a button. After you write these in y equals as two separate lines, you're going to hit second, trace, and then you're going to choose option 5, which says intersect, and you're going to find the intersection point. If you're using Desmos to do this, then you would graph both lines, and you would just go over to their intersection point and click on it, and you can see there's two values. There's an x value and a y value, and our answer is going to be our x values. We want to find x where these two functions are the same. And so our x value is 0.653. So you can find your answer either using the graphing calculator or with Desmos. There's an app for your phone, and also there's the website desmos.com. And so that's how we would do an equation like this. We can't come up with an exact answer when you're using a graphing calculator, but we can come up with the decimal approximation. Alright, that's the whole chapter. Thank you very much and have a good day.